Okay, thanks a lot for the invitation. As you told, today we'll talk about the non-equilibrium properties of systems with collective and long-range interactions. And in particular, I'm going to use entanglement to characterize their dynamics. Now, just as a small introduction, the general setting we have been discussing these days is about the evolution of systems in isolation from the environment. And typically one studies a pure quantum system, like in this cartoon, that undergoes unitary dynamics with a time-independent Hamiltonian. And in general, we know that the system undergoes a non-trivial evolution, which is well understood by looking at dynamics of local observables, meaning that their support is defined locally. And what we know that there is a time regime where dynamics can show very interesting intermediate phenomena. And something else that is very well established is that the asymptotic value of such local observables can be understood through classical standard statistical mechanics. Now, the general scenario, let's say, is the following. In the case of locally interacting quantum systems, is that under very generic conditions, dynamics undergoes a quick thermalization, which means that every time one initializes the system, in every initial state that only has to share the same energy density, then at asymptotic time, the reduced density matrix, locally the system will look thermal. And what we also know is that thermalization can be violated for a long or an infinite time scale due to different instances of ergodicity breaking. The most famous one are integrability, many-body localization. In the last years, we have been learning about fragmentation, quantum scars, prethermalization. And as we know, I mean, the second class is currently the focus of a great attention. And if we want, it's really the very topic of this workshop. So what I'm going to tell you today somehow contributes in establishing long-range interactions also as a source of non-thermal behavior. So what are the systems that I'm interested in? They're characterized by an interaction, two-body interaction between two sites that decays as a power law with the distance between the two. And to be in a truly long-range regime, this power has to be taken to be smaller than the dimensionality. And in classical physics, long-range systems display a plethora of very interesting dynamical phenomena that do not have a counterpart in the standard paradigm we learn at university for statistical mechanics of short-range systems. And examples include ergodicity breaking, slow relaxation, and many others. And what's very interesting is that in the quantum domain, actually, many atomic, molecular, and optical quantum systems are indeed described by collective or long-range interactions. And this is the case, for instance, of Bose-Einstein condensates, cavity QED, trapped ions, and many others. And in particular, trapped ions, which are one of the most promising platforms for quantum computation and quantum simulation, indeed interact effectively through an Hamiltonian of Ising type, that where the interaction is exactly described by this, and depending on the different platforms, they can tune their parameters to get alpha in this long-range regime. Now, this experimental progress obviously has motivated an increase of theory interest in the dynamics of these systems. And in this talk, I will acquire let's say, a quantum information perspective to describe their peculiar dynamics. So when we think about quantum information, of course, we think about the paradigmatic quantity, which is the entanglement entropy, that both at equilibrium and out of equilibrium encodes a very interesting information about many body states. So in particular, if we look at the entanglement entropy of the time-dependent state, we know that this quantity, first of all, somehow limits our ability to simulate quantum dynamics on classical devices, but also it unveils crucial properties of the systems that we are considering. And in the case of short-range interactions, there is a very well-set paradigm for its growth. So generally, so both for integrable or chaotic systems, the entanglement entropy grows linearly in time and then saturates to a value which scales with the volume of the partition that we are considering. And this has been explained with physical pictures, like the beautiful quasi-particle picture of Calabrese-Cardi for integrable systems. And on the other hand, the presence of an extensive set of local conserved or quasi-conserved quantities hinder the growth of entanglement, which corresponds to saturation in the case of many-body localization, or is characterized by its standard characteristic logarithmic growth in the case of many-body localization. But I want to mention that there are many ways to characterize quantum correlation, and another interesting way is through its multipartite entanglement. It somehow answers to a complementary question to respect to the bipartite entanglement, meaning one can rephrase the question: how many parties of the system that we're studying are entangled? How many of them are talking to each other? And a possible way to answer this question is through the quantum Fisher information. Now, this quantity is actually introduced typically in quantum metrology to bound how well we can estimate an unknown phase. And unfortunately, for time constraint, I don't have time to go into the derivation and introduction. Just know that for pure states, like time-evolving states that are the one we're considering, the Fisher information is just 4 times the variance of the operator associated, conjugated to the phase one in principle want to estimate. But of course, we're interested in entanglement, and there have been a series of papers showing a relation between the Fisher information density, so we take it and we divide it by n, and multipartite entanglement. And indeed, if the Fisher information density is bigger than a certain integer m, then one can say that there are at least m plus 1 parties which are entangled. Namely, the quantum Fisher information density gives us the size of the biggest entangled block.
Sorry, Silvia, maybe a silly question that I missed. How this operator O is connected to the state? You say so this is a probe?
That's absolutely a good question. That's absolutely a good question. So the operator in principle, the operator is not connected to the state, it's connected to this metrological experiment, probe experiment that we're making. But since we want to estimate the entanglement content of the state, in principle, one should maximize over all the operators. Obviously, it's a quite hard task. And in general, physical knowledge about the system will tell us which operator to consider. So the standard example is at quantum phase transition, where the order parameter is diverging, and that's obviously the best way to estimate the entanglement content of the system. But it's so from the quantum optics community, this quantity has somehow reached the many-body one, mostly because of this result of Hauke collaborators, in which they showed that at thermal equilibrium, actually the Fisher information is related to thermal response functions, and then this has been generalized by us also on ETH. And this somehow has important consequences. So first of all, it shows that the Fisher information also diverges and obeys universality at quantum critical points, a property that also the entanglement entropy has, but also makes it easier to measure the Fisher information, especially with respect to the entanglement entropy. So what I've been interested in the past few years is studying using these quantities to look at long-range systems. And in this talk, I'm going to consider as an illustrative example the standard Ising Hamiltonian with long-range interactions. And the presentation is based on work done with Alessio De Rose, who is a postdoc in Geneva. And we've been thinking about this model a bit. And I'm going to tell you, and I'm going to start in the first part to the simplest limit, which is the fully connected limit, in which every spin is interacting to each other. And in this case, well, there is an exact underlying semi-classical description that interestingly allows to connect all these different concepts of entanglement, which in principle are decorrelated. And then I'm going to show you how this collective contribution at alpha equal to 0 is actually the dominant one, also when alpha is smaller than the dimensionality. And this holds at least up to a prethermal time scale, which diverges in the thermodynamic limit. And then, if time permits, I would like to tell you about some work in progress with Dima Banin, Rosario Fazio, and Alessio and Tommaso Parolini concerning the fate at infinite times of these dynamics. And I will show you that somehow there emerges a picture
Silvia,
of scars of collective origin.
It looks that there is a question in the chat. Sarang is asking, probably related to my question before, is the O operator an observable or can be anything, probably?
So yeah, it's an observable. In principle, the first bounds that have been proved were restricted to collective operators, which are sum of local ones. And the idea is that the first setting of the quantifier information were interferometry experiments, but then it has been generalized also to non-local operators. But yeah, it should be an observable, yeah.
Thank you.
Okay. So we can start from the fully connected limit, where, as I told you, one can effectively use a classical picture. And this is because for fully connected models, ground states can be visualized on top of a block sphere of radius given by the global spin, which is maximal, and it's n/2. And this means that also the dynamics can effectively be described in a semi-classical way with a vanishing effective Planck constant, which is 1/n. This means that every time that the system is initialized in a localized wave packet with a variance of the order of this effective Planck constant, then quantum observables obey classical equation of motion, at least at short times, before the RMFS timescale that defines somehow the timescale at which quantum interference effects becomes dominant. And of course, one wonders what's the relation of entanglement with such a semi-classical description. And this question actually has been answered now a long time ago in this series of papers by Zurek and Patz. And they were actually interested in understanding the correlation, the entanglement between a system coupled to an environment, and they understood that the growth of the entropy of the subsystem, which is the entanglement entropy, could be understood from the evolution of the wave packet into a multidimensional hyperpancake. And they also said that the entropy was going to be given by the logarithm of this effective wave pancake, hyperpancake. And in the case of chaotic systems, it was growing at a rate given by the sum of the positive Lyapunov exponents, which is the classical Kolmogorov-Sinai entropy. And I'm going to go back on this in a second. Now, I just want to mention that these results by Zurek and Patz were actually confirmed by a series of numerical analytical works in the early 2000s, where people were really interested in understanding the coherence on rather different objects, so focusing on Loschmidt echoes and purity decay. And as you know now, the study of entanglement somehow spread over different communities. And in the high energy community, recently, the Zurek and Patz conjecture has been put really on solid grounds in these papers by Bianchi, Hackler, and collaborators. So in this limit, in this semi-classical dynamics, we can connect the growth of entanglement to the growth of the Fisher information, and also to the growth of the square commutator, which is another quantifier of quantum chaos. And everything is linked, boils down to the classical underlying trajectory. So this is the general prediction for times before the RMFS time. Every time we have a trajectory which is integrable, or the system is initialized on a Km tori, then the entanglement entropy grows logarithmically in time, while the Fisher information and the square commutator grow polynomially fast in time. On the other hand, for systems which are chaotic, or on top of unstable trajectories, the entanglement entropy grows linearly in time with a rate which is the Kolmogorov-Sinai entropy, that is the sum of all the positive Lyapunov exponent, and this is the Zurek and Patz result, while the Fisher information as well as the square commutator grow exponentially with a rate given by the maximum Lyapunov exponent, and this for this square commutator, it's something well established. On the other hand, if the dynamics is, let's say, boring, so in the absence of interactions or for stable classical trajectories, then all these quantities only undergo periodic bounded oscillations. So just to flash how actually one can derive this picture, well, it comes from connecting all the entanglement quantifiers to the matrix describing the quantum fluctuations around the classical trajectory. This is really just a symmetrized matrix of the quantum fluctuations. And actually, in the classical limit, so before the RMFS time, this matrix crucially corresponds to the classical matrix that encodes the flows of linearized displacements and actually encodes all the Lyapunov spectrum, the time-dependent Lyapunov spectrum. So the relations go as follow. Let's start from the entanglement entropy. First of all, one has to identify a bipartition, which in the case of fully connected spin systems will be given by two sets of spins, an A and an B. But this could be even more general. For instance, if we consider the decay model, we can have spins and cavity or more complex situations. Anyhow, everything boils down in computing the reduced correlation matrix, and then one can directly that asymptotically go with the logarithm of the volume of the quantum fluctuations of the reduced degree of freedom. And then also the other quantities meet equivalent descriptions. So the quantum-Fisher information is the maximum eigenvalue of this matrix. One can write the spin squeezing, and also the square commutator that I finally define. It's the expectation value of the square of a commutator between two operators at different times before the RMFS time can be directly written in terms of the matrix elements of the evolutor of the quantum fluctuations. So as I told you, this is general. It's not only for fully connected systems. It holds every time we have a bosonic classical limit. And in the case of infinite range spin systems, the equations simplify even more, and we can write everything in terms of the collective excitations on top of a fully polarized state, where Q and P really represent the transverse fluctuations around the time evolving state. So they are zero for a polarized state, but once dynamics with interaction goes on, quantum fluctuations get squeezed, and one can write everything in terms of this number. So spin squeezing is 1 over n. The Fisher information and the square commutator are proportional to this number of collective excitation, and the entanglement entropy is proportional to the logarithm of this quantity. So let me show you an example in which we study these things, and let me take the fully connected limit of the long-range Hamiltonian I introduced you before. So this classically is only 1 degree of freedom with conservation of energy, so it's integrable. It will not display any chaos. And what we do, we basically initialize our system in one of these regular trajectories, and then we consider a quantum quench. So we evolve with a different Hamiltonian, and we study the different entanglement. So basically, on all the trajectories, the entanglement entropy grows logarithmically in time, as I was telling you. And here we compare the analytical prediction coming from the integration of this classical equation of motion with exact numerics. And I remind you that for this class of systems, the Hilbert space is very small, scales only linearly with the system size because of the conservation of the total spin. So, and you see also the Fisher information asymptotically goes like this square, but for finite system sizes, one reproduces the systems, the dynamics only up to finite times. And now also let me mention that this Hamiltonian also is characterized by a classical separatrix, which is associated to dynamical criticality. And on top of this classical instability, classical separatrix, the entanglement entropy grows linearly in time, and the Fisher information grows exponentially in time. And the rate is given by the eigenvalue of the instability matrix on top of the unstable point. Yes, there is a question.
There is a question by Dominic, so please,
yeah.
Dominic.
Can you hear me?
Yes.
Yeah. Okay, awesome. Yeah, so I wonder about this quantum Fisher information. So you define it at some maximum over some eigenvalues. So I know it defined as let's say for pure state, it's equivalent to the variance of some generator translations. Is that the same thing, or I just wasn't sure?
This is what. No, it's a good question, sir. I wasn't clear. So in the case of fully connected, as I told before at the beginning, answering to the first question, one needs some kind of knowledge about the system to choose the correct operators. Now here, I'm considering collective spin system, fully connected spin systems. So the reasonable thing to think about are collective operators, so sum over all the spins of the single spins. So in this case, the Fisher information is defined as the maximal variance. So also in this plot.
Maximal variance. So the G operator is a variance?
The G operator, yes, the G matrix I told you here before is the variance between the quantum fluctuations. So I can define the fluctuation operator as the distance between, so this is a generic operator, but it could be your spin operator minus the classical expectation value. And then you build a matrix, matrix with them. So
I wonder why you
when you do numeric, because you want the best estimate of the entanglement. So the Fisher, you want to maximize the Fisher information to give the best estimate of the entanglement content.
Oh, I see. So it's not that the definition itself would be a maximum over something. It's more like you take the maximum of Fisher informations.
Yes. Yes. So, yeah.
Okay, that wasn't clear. Okay, I get it now.
Okay, sorry. And yeah, in general, the Fisher information always depends on an operator. So if one wants to estimate the best, one should maximize over something. And in this case, it makes sense to maximize over collective operators.
But then in Fisher information, maximization goes over projectors, over the measurement, right?
There are two steps. So the classical Fisher information has no maximization. So the quantum and the classical always depend on an operator.
Yeah, maybe later.
Yeah, maybe we can go back to this point in the discussion.
Yeah. Of course. Yeah, I'm sorry, because it's always confusing to mix these different concepts. Okay, so but now I told you what happens before the Ehrenfest time. So going back to our entanglement dynamics, and after the Ehrenfest time, entanglement saturate. It's okay.
Silvia, we are having some problem. At least I'm having some problem with listening you. But can you start again?
Are you okay now?
Yeah, try.
Can you hear me now? Okay. So interrupt me if it doesn't work, sorry. So I was just saying that after the Ehrenfest time, entanglement saturate, and the entanglement entropy saturates to a value which scales with the logarithm of the partition that we are considering, while the Fisher information saturates to a value which is proportional to the system size. And this in jargon is called a genuinely multipartite state. And those are the ones that are more useful for phase estimation protocols because they can beat the classical bounds in phase estimation. Okay, so now let's say at the collective level, everything it's quite clear. Now we want to go to the long range case. With finite range, but still very long. So, and the question about the entanglement also was addressed now a few years ago. And the first one to study them, I would say, were in 2013 in the group of Andrew Daly. And they were the first one to report a logarithmic growth of entanglement in the case of long-range clean Hamiltonians. And they reported it as being counterintuitive in the sense that, as I told you at the beginning, short-range interacting systems have linear growth of entanglement. So one could guess that with long-range interaction, things might get entangled faster, distance degree of freedom. Instead, in this case, there was this logarithmic growth of entanglement. And after the results, there have been some attempts to understand this growth, and I hope I will convince you that within this semi-classical perspective, one can really understand and interpret these results. So let me tell you what we do. Let's write once more time the long-range Hamiltonian, and notice that here I'm considering the Katz normalization, which is here in order to ensure the extensivity of the energy, and it's the usual 1/n of the fully connected limit. And then what we do is that basically we expand around the classical solution that corresponds to the zero mode, to the collective mode. We go on for a space and do standard Holstein-Primakov transformation, truncating at the quadratic order, and we obtain an Hamiltonian which is a sum of two terms. And the first term is really the classical collective Hamiltonian we have discussed so far. It's characterized by permutational symmetry, and also from the conservation of what we call the total number of spin waves, and that is the sum of all the spin waves of finite wavelength. And in this case, the classical limit is integrable, so one expects logarithmic growth of entanglement. And on the other hand, we have a spin wave Hamiltonian that in principle is breaking permutational symmetry, so it should bring us away from this block sphere of total S large, because spin waves are generated at all wavelengths by the dynamics. But it turns out that these spin waves are actually suppressed, and this depends on the specific structure of the coupling constant of the Fourier transform of the interaction, which is this F tilde. So this F tilde, okay, again, it's really the Fourier transform of the interaction. And how should it look like? Well, for large alpha, so in the short range case, at infinite alpha, we should retrieve the cosinus of nearest neighbors interactions. On the other hand, for alpha smaller than the dimension, this quantity gets more and more peaked to k equal to 0, becomes more and more a delta function as we increase n. So this can be seen numerically. One can also work out a finer estimate. And this tells us basically that for any finite k, this coupling is actually vanishing in the thermodynamic limit. And this somehow allows us to say that the associated number of bosonic excitations at finite k are actually a quasi-conserved quantity, in the sense that there exists a long prethermalization regime before which these are suppressed. And this holds before this time scale, this prethermalized scale that diverges in the thermodynamic limit. And this is also been found with a different perspective by Takashi Mori. And this says that before this time scale, one can quite safely say that the system will remain trapped near a small submanifold of the full Hilbert space that is only scaling with the system size. And of course, we can try to somehow refine this analysis by looking at long wavelength modes, scaling with 1/n, that could break permutational invariance. And there will be only a finite set of them. And indeed, to study them, we realize that the Hamiltonian describing them is just an Hamiltonian, a set of periodically harmonic driven harmonic oscillators where the drive is given by the classical period. So again, we can perform some kind of classical analysis of their stability and look at what happens at the classical period by looking at the basically at the Floquet energies. And so we know that driven oscillators can either be stable or unstable. And to characterize it, we study it numerically. and we plot the Kolmogorov-Sinai entropy that again is defined as the sum of the positive Lyapunov exponent. So in the case of stable spin waves, this should be 0. On the other hand, for unstable spin waves, this should be finite. And what we find quite surprisingly is that actually these spin waves are almost always stable. So they're always only doing small oscillations, and only in the vicinity of the classical instability I told you before, they can be unstable, and there is a finite layer of instabilities arising at finite alpha. So we now want to restrict to the standard quenches for which spin waves are stable and see how much these impact the growth of entanglement. And to do it, we use the standard bosonic techniques for quadratic systems. And indeed, we see that the impact of the quantum spin waves, it's only yields a periodic oscillation on top of the leading logarithmic growth of the entanglement entropy coming from the fully connected limit. And this is at a spin waves calculation, but we can compare with numerics for the Ising Hamiltonian, and that we did using TDPP. And you see that even for alpha equal to 0.7, which is relatively far from alpha equal to 0, the exact results actually go quite on top of the semi-classical spin wave prediction. And so let me also mention that somehow in this case, the standard quasi-particle picture is failing because of the quasi-conservation of the spin waves. And somehow there is a different mechanism for the entanglement growth, which is coming from the presence of the squeezing of this dominant zero mode. Okay, so this is for this intermediate time regime, and what we have been thinking on more recently is understanding whether this has an impact also at infinite times. So I hope I can take 5 minutes to.
Of course, yeah.
Okay, so somehow we enter in the realm of numerics and we start studying the spectral properties of these Hamiltonians. And we also restrict only to Hamiltonians that do not possess separatrix at the classical level, because I've just told you that in that case, also at the semi-classical level, there are instabilities. So only Hamiltonians without separatrix in the classical limit. So the spectrum of this Hamiltonian is quite anomalous, but first let me recall you a few properties of the spectrum in the fully connected limit. So as I told you, the total spin is conserved, and this means that if I plot the total spin for each eigenstate, I will obtain a very regular pattern. Can also be called the Perez lattice, where eigenstates are characterized by their quantum number, which is the total spin. And now let me mention that the states possessing the maximum spin, there are only n of them, while as soon as the spin becomes smaller, they are highly degenerate. So here, changing colors, I'm representing an increasing density of states, and indeed, each sector has a degeneracy, which becomes exponential in the sectors with smaller system size, smaller s, total s. So we wanted to understand how the breaking of this conservation law affects the spectrum. And indeed, we want to see how these states hybridize. And what we find is the following picture. So this is the usual plot. Here there is an observable entanglement entropy and overlap with a simple state, which in this case is the fully polarized state. And what we see is that the hybridization between the eigenstate happens in a very peculiar way. So there is this relevant structure in the bulk of the spectrum, which we don't know whether it's going to be stable in the thermodynamic limit, but our guess is no. But what's probably more interesting, at least for us, is the existence of these collective states, which actually don't seem to mix and to hybridize with the rest that always also have small entanglement entropy to respect to the rest of the spectrum and high overlap with easy states. So they somehow possess all the properties of many-body quantum scars. So to study a bit better the spectrum, we performed spectral, level spacing statistics. And here I'm showing you the level spacing ratio for different system sizes. And you see that by increasing system sizes, it clearly goes to the Wigner-Dyson statistics. So meaning that the bulk of the spectrum immediately, so as soon as I break the conservation permutational symmetry, immediately becomes has a level spacing ratio, which is Wigner-Dyson. But what we really, above all, what we were interested in is characterizing these athermal eigenstates possessing maximal spin. So to do it, we somehow wanted to get bigger, so to get bigger system sizes. And so we implemented an approximated numerical method, which amounts in projecting our Hamiltonian in a subset of the Hilbert space that possess large spin, because we know that these states have large total spin. And so to do it, we basically implemented, we defined a k Hilbert space given by k sectors of total spin, of decreasing total spin, starting from the biggest, and then for k equal 1, we only have maximum spin, k equal 2, we have maximal spin and maximal spin minus 1, etc., etc. And so for k equal to n over 2, we retrieve the full Hilbert space, but for finite k, the dimension of the Hilbert space scales only with n to the k. And therefore, this k somehow can be thought about a bond dimension upon which increasing, I can see whether I have convergence or not. And to implement it, we use the three representation of the SU2 bases used by the group of Abanin, Scardicchio with Daimler, and they actually were studying MBL, if I'm not wrong. So after we study convergence of the states and they converge with quite well, we were able to get only up to 40 because, if k is big, the scaling can still be problematic. Anyways, so what we find is that these states seem always have high overlap with initially polarized states. They keep having extensive total spin and with only sub-extensive corrections, and that their entanglement entropy, and this is the plot that I'm showing you here, scales with the logarithm of the system size. So here I'm showing you the entanglement entropy for half a system for a single eigenstate, one of these collective eigenstates in the center of the spectrum, and it shows logarithmic growth. And now you see that this logarithmic growth has a clear classical interpretation in the sense that semi-classical eigenstates can be interpreted as stationary states of a given classical trajectory. And I showed you in the first part of the talk that indeed the entanglement entropy after a quench dynamics scales with the log, and this is how one can interpret this scaling. Okay, so I think I'm done also with time. I presented you these dynamics of long-range systems which do not fit in the standard paradigm of short-range interacting cases. And I told you that everything somehow is simple in the fully connected limit, but this allows a nice framework to understand all these different concepts of entanglement directly from the classical limit. And as a consequence, it's maybe that also entanglement entropy for this class of systems might be measurable in an easier way. And then I told you how, this collective contribution is actually the dominant part also for finite alpha, at least before this prethermalization time scale. And somehow this prethermalization comes and arises from the quasi-conservation of spin-wave excitations. And then at the end, I somehow flashed some results about the arise of scars, which have a clear collective nature and a clear classical limit, which is not always the same case scarce. So we have several things still to understand. First of all, the stability of this scarce in the thermodynamic limit, because we are not sure whether it's a finite size effect, and then several possible generalizations. And just to mention that if you we're now triggered on the physics of long-range systems, there is a review coming soon on physics reports on the dynamics and their criticality of systems with long-range interactions with Alessio De Rosa and Nicolò De Feno. With this, I thank you for your attention.
Okay, thank you very much, Silvia, for the wonderful talk. We have time for discussions, so I don't know if Dominic maybe wants, but other people too. I mean, yeah. Are there questions? Okay, so far nobody is raising. Yeah, Dominic unmuted, so maybe he wants to say something.
Yeah, I just want to, if nobody's asking, I'd like to maybe continue the discussion about this quantification information.
Yes. So let me show you this slide because
right.
Maybe it's a bit more clear. So this protocol that is on the top of the slide is general. It's not so this first part, this box, it's not restricted to quantum situations. So one has a state and a black box, and in the black box we have a phase that we want to estimate, and then we assume that the phase will interact, that the black box will just apply a unitary transformation which encodes the phase, and then if the system is quantum, we perform a quantum measurements. Okay, right. So these quantum measurements depend on POVM. And they can be defined in the standard protocol. Okay, now to define the but before the quantum measurements, the protocol, it's also true in classical physics, one can define it. Now, right. In the quantum case, you define the quantum Fisher information, maximizing over all these quantum measurements. But again, this quantum Fisher information will always depend on the operator O. So the quantum, right. Now the process of maximizing over all these quantum measurements, in my definition of the Fisher information, is not even present. I'm already considering the quantum version, which has already maximized over the measurements. Was it, it's not more clear?
Right, then I wonder what is the maximal eigenvalue of G? That's coming from a different maximization, right? Or is it the same maximization?
So this Fisher information still depends on an operator O, which is the one that is conjugated to the phase. So in principle, we have different Fisher informations for different operators.
So you are maximizing over encodings.
Yes, I'm maximizing over the direction, the collective direction of the spin.
I see. So there are two let's say operators or measurements. One is related to the O, which is the encoding operator, and one is connected to how the phi is extracted by projective measurement at the end, right? Exactly. So the quantum Fisher information is the one optimized with the letter, but it still depends on this O, but you also maximize over the O.
Yes, but if I take the definition of the Fisher information, this maximization procedure over all the measurement is already done. So when I write variance of the operator, I don't even think about these measurements anymore.
So what was the reason by maximizing over this over these encoding operators? What's the argument for that?
Well, I guess that once you have a quantum state, you might have different outcomes depending on the operators, and the way to uniquely define it is by maximizing, I would say, but I'm not.
Yeah, just wonder in the context of your talk, Why would you
no,
want to do that?
okay, no, in the context of my talk is that I want to best estimate the structure of the entanglement of my system. So I want to give the best estimate of how it's entangled. And so in this case, the entanglement will be given by this maximal fluctuation. So I want to consider which is the direction where the quantum fluctuations are fluctuating the most.
Oh, so the entanglement is upper bounded by this quantification information.
The multipartite entanglement, yes.
Ah, interesting. Okay, I didn't know that.
They're different concepts in principles, and indeed in short-range interacting systems they're not always related, but for special kind of systems, like in this classical limit, so everything boils down to the same quantity. So they're actually related, the bipartite entanglement and the Fisher information.
Mm-hmm. So you showed some theorems. Sorry, I maybe missed this. Is there some theorems?
I mean, we can derive. We I don't know if it's a theorem, but we derive yes some equations, some relations between
Fisher information
and the entanglement entropy. Yeah.
Oh, entanglement. Okay. Very interesting. Thank you.
Okay. Any other questions or comments?
Can I ask a question?
Sure.
Okay, so if I remember correctly, the Fisher information for the classical system is related to the parameter inference out of the random sampling. So in your quantum version of Fisher information, is it also related to such inference?
So I'm not an expert on this, but I know that now the Fisher information is used a lot also for inference, and it's also used a lot also for NISC, this for estimating and optimizing parameters. And in particular, I'm interested in understanding it in relationship to the entanglement. So I'm more focused on, where is it? Yes, on the relation with the structure of the blocks of the entanglement. But I think also in the quantum case, there is a relation to what you were saying. I have in mind some references, but I'm not an expert. If you want, I can.
Actually, the reason I am asking this question is that in some page I saw Kramer-Rao inequality. So actually, that Kramer-Rao inequality is extremely useful for classical thermodynamics, which lead to the so-called thermodynamic uncertainty relationship. So I don't know whether why do you mention this Kramer-Rao inequality?
Yeah, no, absolutely. This is I mean, I think it was the one of the reasons why they also introduced this quantum Fisher information. So the Kramer-Rao bound that you're referring is the following, no? In which one can bound the variance of the phase of this protocol with this M, where M is the number of measurement and the Fisher information. And now in the case of separable systems, in the case of classical states, so if rho is separable, then the Fisher information is only N. So one says that the best way to estimate your phase, I mean, there is a bound which is called this short noise limit that says that this variance, this minimal variance goes like 1 over square root of N. Instead, if your system is entangled, and this is where the quantum Fisher, why we're looking at the quantum Fisher information, then the Fisher information scales like N square, and then you get the Heisenberg limit. So this is to say that yes, in the quantum case, the quantum Kramer-Rao bound can be extended. Then actually, it's very it has been extended.
Okay, thank you. I should study the meaning of this quantum feature information better. But anyway, thank you very much.
Other questions or comments? It looks no. So let me ask a very quick question, and then we can probably finish. Can you go to the when you say that a result is counterintuitive, this logarithmic growth when you go to long range?
Yes.
Now, if I understood properly the second part of the talk, you say that this counterintuitive logarithmic growth is because you have this, let's say, scarce states, right? Now, the question is, to this, all this second part of the talk and the result, is it crucial that your model is clean, that there is no disorder, that J is just a number?
Well, so yes. No, in the sense that it's crucial to have, one can imagine generalization in which maybe the external field is a bit disordered, but the point is that one needs a strong SU2, so you need an underlying SU2 symmetry, no? So the crucial fact is that your initial Hamiltonian, where is it? This initial Hamiltonian conserves the total spin.
Okay.
And you could generalize it saying, okay, consider different species, but then you have to send S to infinity. So you can devise a different classical limit, which will probably not be integrable because you will have a more degree of freedom. And
okay.
But in the case of spin 1/2, that's the only case. But if you can consider several species with different coupling constants.
Okay, thank you. Okay, so if there are no other questions, maybe we can thank the speaker again, and probably this is a good moment to stop recording.